This is class 221B, group 6. We are doing our lesson 6 assignment. So let's go. You guys all got part 1, right? That wasn't any problems with that.
Yeah.
Okay, however, I do have a question about this. I still do not understand the difference between central limit theorem and law of large numbers. I mean, do any of you guys have like a easy way of knowing the difference?
Yeah, that's a good question actually, and it's important. So the central limit and law of large numbers have similar ideas. They're talking about two different things. Law of large numbers talking about accuracy of the mean. So you say you're doing a sample population, and your population of what you're looking at is America, but you're taking a sample. You can't take everyone in America. You take a sample of like 50,000 people. The idea is the more people taking in a sample, the closer you get to the actual population means. So it's an accuracy thing. So if you're looking at, okay, the rate of cancer people and lung cancer deaths in America, you probably can't get every data on that. You probably take a sample of maybe, that's a bad example. Let's say we're talking about people under the age of 8 who have birth defects. Anyone want to come up with an example?
Just go with that. I think that's fine.
All right. Well, the idea is your population is a big deal. The big deal in larger numbers is the population versus sample population. You understand that difference?
Mm-hmm. Population. So sample population is like 100 BYO students is one sample, but then you do that like multiple times, and that's your.
Yeah. So population is the population mean is referred to what you're trying to make a sample of. So you're trying to make a sample of all the BYU Idaho students who their ages, but you can't take everyone's age. So you get a sample of 100 students, and you do that multiple times. And the more times you do that sample of 100, the closer your mean that you get at the sample is going to get to the actual mean of the population. That's law of large numbers. The central limit is different, though. Central limit isn't talking about the accuracy of the means. It's talking about shape. So bell shape. The idea is that if you there's two. So let's look at this thing right here, number 6. So what we're looking for in central limit theorem is that the larger the sample size and the more you take, the closer it's going to go to normal. And you know what normal means, right?
Yeah.
All right. So the idea is if the sample population is normal, so if it's a normal shape graph, the population, then if the sample population is what you're taking is normal, then the central limit theorem is that your means. Central limit theorem is talking about the means and the means, and so part of it is let me use this.
And so, like, it's basically what the central limit theorem is saying is like, if is like the means of the means is going to be normal if you have a big enough sample size, if that makes sense. Whereas the law of large numbers is just saying a larger sample size is going to have a mean that's closer to the population mean.
Yes, that makes sense.
Okay.
Sorry for over-explaining.
Oh, no, it's fine. It helped a lot too. It helped me because I wasn't super getting it.
Yeah, so large numbers, what I get it is accuracy. It's the closer to the realistic mean, the more you take. So like the head-tail thing, you could have 7 heads in a row at the beginning, but you take 1,000 heads and tails, it's going to closer to a 50-50 ratio. So it deals with the probability that you get theoretically being closer to the actual one. I like to use that example, heads, tails.
And this is really based on a random sample. Like, so.
Yeah, but the central limit again is the idea of the distribution is normal, so it's symmetrical, it's bell shaped, both sides equal to the mean. So if you have, say, we'll look at this for a sec. This graph right here, this is normal. But what they're at. So let's start on this. So starting on number 7. What we need to do you guys figure out how to do that, the random integers thing?
Yeah. just pick 5 random ones from those 30.
So you go to random.org or you cut them out and paste it. The idea was that they randomly give you 5 integers. You can actually take so I can pop it up for you. Do you guys go get that?
Yep.
All right. So what did you guys get for your 5 integers? I'll pull mine up too.
Oh, I don't know which numbers I got.
No, I'm sorry, the mean of your sample.
My mean was 48,780.
All right, I got 43,320. So I was a little on the low side, but not unusual.
Yeah, because I got 45,200.
You're close to mean then.
4,000. Wait. 444,000. Wait, no. Sorry.
400.
Ah.
So what they're looking for is, they asked if it's unusual. The video kind of explained it, that it really can't be unusual unless it's like right over here. And so if you somehow had a mean that was in the 40,000, then yeah, it was unusual. But the idea is that even if your sample size here, the more you may take one here, and the next one you take is down here and here. As you take more samples, they all equal this thing. That's what the central limit is talking about. So question C is to be unusual, not really. Again, it has to be. If you got something that wasn't technically possible, that would be unusual. But anything in this area is good. Question A, you have to compare it to 3 other individuals. So this is what they're talking about, the idea of the sample only having one sample. And this is why the central limit theorem is important, because if you take one sample and you make it, say, I did 43, that's your mean. The mean of the normal, the larger number say the more samples I take, the closer I'm going to get to this mean of 47. But the central limit theorem is going to say, okay, my mean of my sample, the distribution of my graph is normal, because it has to be normal because the population is normal.
Yeah. So
going back to part 1, there's 2 ways it's going to be normally distributed. So if your sample population, and we're talking about like population, not your random sample, the sample population is normal, it's always normal. And if not normal, say this graph was left skewed, so it's all up here, the higher the number of samples you take, the closer that graph is going to get to normal.
Mm-hmm.
All right. So let's do this idea with 8. What is the shape distribution for the sample, meaning for all such samples?
So were we supposed to like guess on this one, like just by the numbers that we have there?
No, actually, this one is sort of a trick question. It tells you in the book and the videos that the shape of the if the shape of the distribution, it tells you up here is normally distributed, then it's always going to be normal. So if
I didn't even see. Yeah, I didn't put that together. Okay.
Yeah. So they talked about in the video the idea that if something's normally distributed, to tell your population normally distributed, like up here, the DMT test normally distributed, then your sample is always going to be normal, no matter how little you have.
Yeah. Okay, makes sense.
That makes sense.
Yeah.
So I say the sample means for all such samples. How do you know distribution of sample has the shape? Again, because the distribution is normal. What is the means of the sampling of sample mean score for all such samples? This is where it comes into the theory, the idea that the mean of the mean is the mean of the population. So the mean of all samples is going to be the mean of the population. No matter if it's left skewed, right skewed, whatever, the mean is always going to be the same.
Mm-hmm.
So a good thing to remember is that the mean is always going to stay the same. And then if it's normal or not normal, that's also going to stay the same. The standard deviation is going to change, though.
So the standard deviation. Go ahead.
That's what threw me off, because like I was like trying to think. I was like, well, if the mean stays the same, how could the standard deviation change? And it kind of started to make sense, but like it was just
So we'll get into in this question right here. What is standard deviation distribution scores for all such samples? So this is where you use the formula that you get the standard deviation. Let me see if I can pull up the formula. The standard deviation
over the square root of n.
Yeah,
right?
That's right. Yeah, I did this yesterday. I've been doing other stuff since then. So
you're good.
All right, so part of this, and part of the reason we say it is close to normal, your standard deviation right here is 113. That's the population standard deviation. The reason this is going to be different is the standard deviation of the sample is not actually looking at that standard deviation. It's looking at the differentiation between the sample and the means. So if you say this to 35, that means that it's 35 away from the standard deviation. So that your graph is 35 standard deviation from the population's graph. Does that make sense?
Mm-hmm.
So part of it is we only took 10 students. But if we had taken 1,000 students or more, we'd gotten closer to this 113. So that's where we talk about accuracy, the idea that the more sample people we take, the closer the standard deviations can get to the normal.
Yeah.
Because standard means is always the same. This is a straight line. The standard deviation is how far you are from the mean, and that's going to fluctuate depending on how large your sample size is.
Yeah, if your sample size isn't it like if your sample size gets bigger, then your standard deviation is going to get
closer to the real one.
Yeah.
So it wasn't explained well, but you test it out. Yeah. So the standard deviation right here is 113. This is going to get sample deviation. The more you do it, so if you take infinite samples, it will equal 113. Because it's that's where the large numbers. Central limit theory, the idea that that the standard deviation is trying to get closer to its original, but it has to go depending on the sample size. So does that make sense for you guys?
Actually, it gets smaller if the standard deviation.
Sorry, I meant to say it's closer to 1.
Yeah. Okay.
So I was like confused. I'm still kind of sleepy.
No, you're fine. You're fine. You're fine.
I got a headache. So yeah. So this 35 is actually meaning that you are because when you look at the standard deviation that's really 1, that's what you want to have.
Yeah.
Because that would be like the
standard deviation of all the means to be very far from each other. You want them to be close.
Yeah.
So you want that standard deviation of the means to be small.
Yeah. So if you got a sample size that was 1.3 or something, you have a very good sample.
Mm-hmm. Okay.
But if you have a sample size of like this 35, you probably need to take a larger sample.
Okay, makes sense.
All right. Let's go into the group quiz. See if there's any weird questions like last time.
Oh, by the way, one of those questions that we took last time that we got wrong.
Yeah.
It was asking for for us to put it into a percentage.
Oh.
Put it into decimal form.
Okay. Yeah, that wasn't clear.
Oh well, I'll take an 80 whatever percent.
Yeah, 85 is fine. Bioscience is supposed to be like the hardest class in math, so. Well, no, sorry, calculus is, but it's supposed to be hard, so.
Stats is just very tedious. That's what I don't like about it.
Well, stats is definitely dealing with accuracy of stuff. So your goal in stats is to have it very accurate, and so not that other math isn't, but it's taking large amounts of data and finding an accurate number. That's just time consuming.
Mm-hmm.
Okay, good is pulling up.
All right, you guys ready?
Just 1 second. All right, I'm good.
Okay.
I'm not there yet, but okay. Yep, ready.
All right. So question 3: when you're taking a sample size of n equals 5, what is the shape of the distribution of the mean histogram when the population is right skewed? So
Right
this
skewed.
is go ahead.
I was just gonna say to be skewed right.
Yeah, well, that's because the population sample is not large enough. They mentioned when in the book that if you so like question 4 is the example. It can be normal because of a high enough population. The math teacher said if it's over 40, you can consider it large. 100 is large enough, but say if you're taking 5, that's not large. It goes to this.
Yeah, here in the book it said if it's almost normal. And the sample population or the sample size can be about 5. If it's heavily skewed, it'd be about 30. And if it's tremendously skewed, it would be different. But he said for this class, technically, like we would just assume if it was 30 or above, it would.
Yeah. Well, and again, it all depends on what population you're looking at. If your population in the United States, everyone in the United States, that's 300 million. You got to talk about something big enough of a sample size to make a realistic example. But then we're just talking about average stuff.
Okay. Yeah.
But that makes sense. So if you decide you're looking to look at the cancer rate in people, you would have to calculate what is the population cancer and what is the sample size that would be a good ratio that would be considered large. So not simply 5 cancer patients, but probably 5,000, 50,000, because it's a higher number.
Mm-hmm.
Anyway.
Makes sense.
Yeah. So 5. So this one is just asking if 5 works when it's normal. That's correct. Again, we said that's.
So we said 4 was normal.
We said 5. So if it's 5, if you have a distribution that's normal populated, then you need to have at least 5.
For question 4, we said that was normal though, right?
Yeah. Sorry.
Okay. Yeah. Okay. Perfect.
Yeah. So the idea is if it's 5, if the sample size is 5, then the distribution parent has to be normal. If it's 30 or above, it can be weird and it can still be normal.
Okay. Perfect.
So like this one, even though it's 100, it's still normal parent population, so it's still normal.
Okay.
Just getting this testing that. So
So 6 is normal also.
yeah, so 6. We all at 7 then?
Yeah.
All right, this one's a little confusing because they're talking about sample size. Essentially, population normally distributed doesn't matter. Sample size is always going to be normal. So the first 2 are normally distributed. That's fine. It can't be small sample size when it's right skewed because that's too big of a skew, but large is fine if right skewed.
So the first 2 and the last one.
Yeah, so you're looking at when is it normally distributed, and that is just what we talked about up there.
Yeah, makes sense.
It says, which of the following gives the best explanation of the central limit theorem? Let's see. I think it's, well.
Give me a sec. I just can't read all these.
Yeah.
I think it's the last one.
It's kind of confusing because some of these seem right.
Yeah, I think
we can narrow out the middle one because that's talking about different theory.
Yeah, I think Camden's right. I think it's the last one. Just because the second to last one, so C, is talking about the law of large numbers, I believe.
Yeah, that is large numbers, and A only talking about as normal. I think the best one is the last one. You okay with that then?
Yep.
Yeah, I guess something you can think about to distinguish the difference is the central limit theorem is talking about the shape of the distribution of sample means, and the law of large numbers is just talking about like how your means will be close together.
Yeah.
So.
Yeah, no, larger numbers talking about getting accuracy closer to the realistic mean, and central limit is talking about the shape of the distribution. So the best way to remember as central shape, a large number accuracy. That's what I learned it.
Perfect.
All right.
So this next one is 10.
Or 9?
Yeah.
Okay, sorry, you're calling question 9, but the answers.
So question 9 answers 10.
Yeah.
Because the sample mean is always the same as the real mean. That makes sense?
Yep.
All right. So we've been talking about this. So the regardless distribution population, the sample size is large, over 30, will be this distribution. We talked about this is normal. Everyone agree?
Mm-hmm. Wait, what was number 10 again? Sorry. Number 9 is 10, but what's...
So 11 is talking about what we talked about before, that the larger the sample size, 30 or over, we can consider it normal because it's a large enough sample size. The central limit theorem says the larger your sample size, the closer distribution gets to normal.
But for 10, he's asking, and so that would be like, to do that, you would do the standard deviation divided by n, so the sample size, the square root of n.
Okay, so I skipped 10. That's my bad.
So it's 1, really.
Yeah, the standard deviation 6 divided square root of 36. That's 1. Yeah. So there's only really 2 formulas you need to know this lesson. It's that the formulas for like math things. So like the mean of the sample size is always the mean. That's the big one. And the standard deviation is the standard deviation over sample size, square root of that.
Makes sense.
The last one will be the central limit theorem.
Yeah.
There was one I didn't answer, actually.
Which one?
I think it was 5.
Let me go back.
It's normal.
Yes. When it's normally distributed population, it's always going to matter sample size.
Yeah, okay.
Okay, so 11 and 12. Is there only 11 questions or are there 12 questions?
There's 12.
And okay, so got it.
All right, I'm gonna see what the answers are. You guys want to wait a sec.
I got 100%.
All right, cool. Jump the gun on me. All right. The real question is, do we all understand all of this? Is this making sense?
I think so. That quiz definitely helped. So.
Yeah, I think the videos are really key with this class. Like sometimes reading it just does not click, but once you see look it through it, it helps a lot.
So the teacher posted a video himself that explained the difference between central limit and large numbers. I recommend watching that. He talked about that.
Where did he post that at?
Oh, sorry. I am scatterbrained today. I think it may have been last lesson he posted about the app. Give me 1 second, I'll figure it out.
I always get a text like notifying me about like having done that quiz, and I always forget that I get those, and so I'm like, oh, I got a text from someone, and then I see it, I'm like, oh, yeah.
I hate it because like mine like reminds me when I have stuff due like 2 days later, and so like every night at like 11 o'clock, my phone goes. It's like, oh my gosh.
You can go in there and you can take those off. I had to do the same thing because it bothered me so much.
Especially if I'm like in bed already, but I'm not quite asleep, and I hear it vibrating, and I'm just like, oh man.
I think what a video is. Because he mentions in his introduction of lesson 6, he made a video about it, but I can't find where the link is. Did you guys find it?
No.
I will send him a message and ask him if he put that up.
All right, guys.
All right, I'm gonna stop the broadcast now.